Welcome to my tutorial on processing oscilloscope data during cooling and rewarming with applications including avoiding ice during cryopreservation. Okay, so here's the objective, right? We want to collect temperature during fast transient cooling or warming process. I'm showing an example of such a process on the left here where for the case we had, we were rewarming a sample on cryomesh, which has a very high convection coefficient, and consequently, especially for thinner samples, fast rewarming rate going from minus 100 degrees Celsius or below to nearly the temperature of the surrounding solution within 5 seconds. So this is not something that can be measured using Bose thermometers. So we are using an oscilloscope that can detect at a really high sampling rate. And here is the experimental process. You're welcome to pause to see all the things I did as a part of the setup. But the main idea here is you can see the laptop on the very left. You can make out its edge is connected to the oscilloscope near the middle here, which in turn is connected to a thermocouple, which in turn is connected to the sample. Zooming in on the sample and the tip of the thermocouple, I recommend something like this, where it has good contact with the bottom of the sample. So in this case, it's engineered heart tissue is the sample. You can see the tip of the thermocouple, which is where the measurement is occurring, is right underneath the tissue. And ideally, this is, very firm contact between the tissue, the thermocouple, and the mesh beneath it, trying to recapitulate what would happen in the actual scenario when there would be no thermocouple interfering with the heat transfer resistance. Of course, there's going to be some interference, and I get a good deal of variation when doing these measurements, something like plus or minus 50% warming rate. One measurement could be a warming rate of 6,000 degrees Celsius per minute. The next, it could be 10,000 degrees Celsius per minute. And so I do think stuff like this, it takes a good deal of practice to even get it working in the first place. And then probably some more refinement would be needed, maybe soldering these things on, or I don't know what would be needed to get more consistency. But at any rate, this is what I did. And I want to talk through the process of analyzing these data in case anyone finds it helpful. So the oscilloscope data that I recommend outputting is data in CSV files because it can be processed in Excel using my spreadsheet. I think this is probably the best way to do it. So there will be the CSV file outputs. You're welcome to reach out to me to have, if you want to know more about how to get the settings set up for this. But essentially, you want to set it up so that during the warming process, which should be within 5 seconds, at least for a lot of what I and others work with, these samples get rewarmed fast, so it is within 5 seconds. At this sort of sampling rate, fits all the data nicely into one sheet. You notice that it's almost out of rows in this sheet of the spreadsheet, not too far to the very end of the spreadsheet. So the software definitely will output more spreadsheets if you keep the data collection going, at least if the settings are right. If the settings are wrong, you may need to change the settings so that data doesn't get cut off from this spreadsheet, so it actually the software can output multiple CSV files. But at any rate, I happen to know that the curve that contains the warming is in this spreadsheet, and one of the quick ways you can check for that here is it goes from about minus 4 millivolts here to about 0 millivolts at the very end. So it goes from a very cold state to an ambient state throughout the process. So this is looking like we have we're going to capture the warming in these data here. And the thing I recommend is copying and pasting this into the template I have. So I have a couple templates that I'm happy to provide. The one we're interested in here is the rewarming one. I also have some cooling templates. This is for fast cooling. And then these are for slow cooling for 70 seconds and 160 seconds. Since these are rewarming data, we'll use this template. Which takes some time to load. There's a decent amount of data in here. Yeah, I can also provide a spreadsheet that has all 4 of those in one, though that takes even longer to load and work with. All right, and the place to paste it in where this spreadsheet is set up to process is if this is pasted in starting at A1. So as soon as that gets pasted in, this is basically is all you need to know to to use the spreadsheet I've developed, because at this point it's going to output what people often care about, which is the warming rate in the ice regime. This is calculated at 7,800 degrees Celsius per minute. This is a reasonable value for 1 millimeter thick tissue on a cryo mesh. And then also it's going to, just to give you a sense of what's going on here, it's going to display the warming process starting near the beginning of the ice regime, so near minus 100 degrees Celsius. It's going to display that curve. Okay, so how is it actually doing this? I don't think you need to know most of this to actually use this file, but be good to know. So okay, we have data in seconds and millivolts here. You might notice that some of this millivolts data is weird slash wrong slash not realistic. I mean, this doesn't even have a value in it. So at first I just removed everything that didn't have values. So I just, replaced it with that. So that's what this column is doing. And then I smoothed all of the millivolts data. You'll notice that somehow, this is, the very first data point is like minus 14. Not realistic whatsoever. Neither is 9, and so on. And so I'm just smoothing out all of those data points so that I'm not so that we're not, especially when we're like, if you want to show these final temperature data, you don't want to show just a bunch of noise. So it's processing now. So this smooths it every 5,000. That's what I have it set up for. In my methods development, that seemed like a good number. I can talk about how you can set this up in an efficient way. But at any rate, I have it set up so that, if you paste that data in, these are going to automatically populate every 5,000. And there's some clicking and dragging you can do if you want to change this away from 5,000. But at any rate, that's, once the millivolt data is smooth, and then we need to convert that millivolt data. I'm using an equation based on published NIST data. That I guess I'm not going to get into the details there, but that's the objective of this column. And then I found that some adjustment was needed to make this as, you could think of this as a calibration. I kind of did a 2-point calibration with what I knew the actual value of liquid nitrogen to be, which is minus 196. I found it was a little off on the low end. So I adjusted it. It was, only 60 degrees Celsius off. So this is not a huge thing, but it's kind of of medium importance, I would say, just to make sure that the temperature values are going to come out in a realistic way. I think the reason I need this thing, because you might ask, this seems like the calibration. Why do you need kind of a second kind of calibration equation? I think what's going on is that, in the ambient environment, this should read 0. The millivolts should read 0, right? In our process, we're taking it away from that ambient environment in the negative direction. And so there are going to be, and like the outliers and like the data is going to be randomly distributed about the mean, right? But the machine itself has a certain cutoff. And I think the cutoff is like minus 50 millivolts. So that's actually probably what's going on with these things. This might be something, that's minus 60 millivolts that might factor into the ultimate average that we're smoothing. And so, but we're more likely to eliminate those that are, on the low end, because we're starting on the low end, like we're at minus 4 instead of 0. So minus like 54 would get eliminated, but not like plus 46. And so that kind of drags up this average. This average, I think, is probably a little bit higher than it should be. Maybe it should be minus 4.33 instead of minus 4.28. I don't know. But anyway, I think that's why I needed the second adjustment. So that's the second adjustment I have. Welcome to perform your own calibration, of course, and check that. And then some of the rest of the stuff is for calculating the warming rate in the ice regime and plotting it. So here are the parameter values. So this is what I've used to calculate the warming rate. So this is, a reasonable choice for where ice formation would be expected to start. You can make an argument for a slightly different value than minus 100 and, put in whatever you think is best. And this is the melting point of the CPA I was using. So I set that to minus 35. I could go ahead and change that if you think, just if you want to customize that yourself, and so on. And the way this is working basically is that it's calculating the warming rate in two ways that give the same answer. This is, I guess you could think of it as just a double check. So one way is what it's looking at is like, okay, where did we start and what time did we start? That's going to be defined at 0. And then where did we end? That temperature, what time did we end? And then we're simply taking the difference in temperature divided by the difference in time. So there's that way. And the other way, which gives the same answer, is just what is the average rate in all the data in that range. So that's just, two ways to, just to confirm with yourself that you have the right answer. And the other thing, just to know about what I'm doing here is, you might notice if you look through this column that it's like, minus 130, minus 130, minus 130, minus 130. I didn't want to just like plot a flat line to begin with. So I have the spreadsheet set up so that it's basically plotting when the warming starts to happen. And also it's like, calculating the warming rate when the warming starts to happen. And it does that via formulas, via basically this formula. It's just checking this cell to the left and so on, and to see if where the warming's happening. And then, this is just identifying when the warming will happen and plotting all that accordingly. And then I guess the other thing to explain is that because we're having some offset, the actual warming didn't start till 2.5 seconds. It's going to plot the first 4 seconds of data following the warming. So it would plot from 2.5 to 6.5, but we don't have that much data. The original spreadsheet I copied over data from is from 0 to 5 seconds. So we don't have data beyond 5 seconds. And so this is just going to plot as a flat line here. I don't really care about that one way or the other because I don't care about data beyond minus 35 because what I care about is the warming rate in the ice regime, and everything, past 1 second basically is not in the ice regime anymore. But just to explain what's going on there, that's what's going on there. And I think, if you care about these sorts of things, maybe you can input experimentally what you found with, a thermometer near the the oscilloscope. So maybe it was, you found it was minus 110. And it's like, okay, maybe you can get maybe a sense of your error there and so on. I think I had this here just to help fine tune this conversion a bit more. This voltage to temperature conversion. So it's using this V offset, but how do you get the V offset? Well, it's dependent on this reference temperature, and there could be maybe your reference temperature is actually like 2 or something. I think this is related to what I was doing with that. I think there's there are different ways you can do this. I think at one point I was investigating using a fitted equation. That's an option if you want to plot this with a log plot and analyze the data that way. This probably has corresponding values using maybe the A and B values here. So that's just a different approach. But at any rate, the the method I recommend is this one where you just like, copy and paste your data here, and then you could just copy this warming rate and paste it into a different spreadsheet, aggregate all the data, aggregate all your replicates to get a sense of what your warming rate is, and similar for cooling rate. So that is the basic method. Hope it was helpful.